Hello students, I hope you are doing well and set for today's session, that is cubes. In this class, we will discuss with the basics of cubes, normally the types of cubes in which we cut the cubes and it is divided into some pieces. So we make some cuts and then it is divided into some pieces. This is to be discussed. These type of questions are normally appearing in LR section. Okay, and the handout to be covered here is LAHO 1031313. Fine. So let us start here. First, introduction of cubes and cuboids. So what is cube? This is a solid figure. Okay, and in which length, breadth, and height all are same, as you may be aware of it. And cuboid, this is a solid figure in which length, breadth, and height all are different. Fine. So this is the definition of cubes, and these are just the basic things required for LR. Now Euler gave some formula related to the number of faces, number of vertices, number of edges. Okay, number of vertices, if I talk about here, I'll get here the number of vertices. So number of vertices is how much? Just look at this. 1, 2, 3, 4. Okay, and behind and below it there are 4 more. Okay, so this is just behind this. So total number of vertices is how much? 8. So number of vertices is 8. Now just look at the number of faces. Number of faces here 1, 2, 3. Okay, so 3 are just visible to us, and opposite to these 3 there are 3 more faces. So opposite to this, one face is this one. Opposite to this, another face is this one. Opposite to this top, this face is here. Total number of faces is how much? 6. So 8 vertices, number of faces is equal to 6. Now look at the edges. Edges, if I suppose this is your y-axis, this is x-axis, and this is z-axis. So just look at this one, this cuboid. Okay, cuboid is also having the same. So suppose this is x, this is y, and this is z-axis. Fine. So if I talk about x, how many edges are there? 1, 2, 3, and 1 behind it. Fine. So there are 4 edges as per x. Similarly, as per y, 1, 2, 3, and 1 behind it. This is, there are 4 as per y here. Similarly, if I go for z, 1, 2, 3, and then 4. So as per all these axes, there are 4 edges each. So total how many edges are here? 4 into 4, 4 into 3, that is equal to 12, or 4 plus 4 plus 4, that is equal to 12. So number of edges is equal to how much? 12. And Euler give the formula 8 plus 6 equal to 12 plus 2. So 8 plus 6, 14, 12 plus 2 is equal to 14. So this is the formula we have. F plus V equal to E plus 2, where F is the number of faces, V is the number of vertices, E is the number of edges. I hope this is clear. Number of faces we have 6, as we have discussed here. Number of vertices 8, as we have discussed. Number of edges 12, and that makes this equation complete. That is here total number of edges plus 2 equal to number of faces plus number of vertices. I hope this is clear. Now next I am going to start here. The cubes are made with cuts here, and it is divided into some pieces. So suppose I make one cut. So if I make one cut, in how many pieces can a cube be divided? Okay, obviously 2 pieces. So if I make one cut, in how many pieces it can be divided? 2 pieces. This is very clear from the figure here. And the first one is upper and second one is lower one. So total number of pieces is how much? 2. Now if I look at this pattern, this cut is made along this edge. Okay, and one cut gives us 2 pieces. So can I say here the number of pieces along this edge is equal to 1 more than the number of cuts made. So we can also write it as number of pieces equal to 2, and that can be represented as 1 plus 1. We will check We will check this type of pattern for the next example also. We will try to observe, try to conclude from this one. Now, suppose I make two cuts. If I make two cuts, in how many pieces can it be divided? Okay. Now, if I make both the cuts along one direction or along one dimension, in how many pieces it can be divided? So, as we already have seen, okay, that number of pieces along one dimension is equal to one more than the number of cuts applied. So, suppose both the cuts are applied along one dimension, the number of pieces is equal to 2 plus 1. 2 plus 1, that is 3. Okay. So if this is the case of one dimension, let's look at this. This is clearly visible. And we have here first piece, second piece, third piece. These all cuts are made along one dimension. Okay. So number of pieces is equal to 3. 2 cuts, 3. So the observation, the pattern is remaining to be same as we have just discussed in the previous slide. And the number of pieces is equal to and written as 2 plus 1, that is 3 here. Now, this is a possibility of making cuts. Now, these both the cuts can be applied in two dimensions. Okay, and when two dimensions, two cuts are applied, then one cut along each of the dimension, and along those dimensions the number of pieces is equal to 1 plus 1, 2. Okay, so two pieces in each of the dimensions, and total number of pieces will be 4. Just look at the figure here. Okay, so if these cuts are applied along two pieces, one cut is applied along this piece, this dimension. So how many pieces? Two pieces along this one, and one cut here. So two pieces along this one. Total how many pieces are here? So just count here: 1, 2, 3, and 4. Total number of pieces we have. How many? 4. And if I go with the pattern, one cut gives us two pieces along this dimension. One cut gives us two pieces along this dimension. Total number of pieces can be written as 2 into 2, that is equal to 4. Or 1 plus 1 into 1 plus 1, that is equal to 4. Now, what the observation we can make here? First observation, as we have just seen in the previous slide, that number of pieces along one dimension is equal to number of cuts plus 1. Okay. Now, if number of cuts are applied in more than one dimension, then the number of pieces along those dimensions are multiplied to get the total number of pieces. Just in this case, we have two pieces along this one, two pieces along this one, and 2 into 2 is giving us 4. So 2 into 2 is giving us 4. So this is another observation, another conclusion we can make here. That is, the total number of pieces is equal to the number of piece multiplication of the number of pieces along the dimensions. Okay, so in this case, we have two pieces along this dimension, two pieces along this dimension. Total number of pieces is 2 into 2, that is equal to 4 pieces. And number of pieces along one particular dimension is equal to 1 more than the number of cuts, that is number of cuts plus 1. This is the conclusion we have made till now. Now I am just going for the next example, that is, suppose I apply 3 cuts. If 3 cuts are applied, there is a possibility of all these 3 cuts applied along one dimension. Fine. So if all these cuts are applied along one dimension, then the number of pieces along that dimension is equal to 3 plus 1, that is equal to 4. Fine. So if these all cuts are applied along one dimension, just look at this here. Number of pieces along this dimension is equal to 1, 2, 3, 4. Total number of pieces is equal to how much? 4. That is 1 more than the number of cuts applied. Fine. Now, if these cuts are applied along two dimensions only, obviously the possibility will be one cut along one dimension and two cuts along the other dimension. So if that 2 and 1 is distribution, then it looks like this one. So if these 3 cuts are applied along two dimensions, 2 cuts along one dimension and 1 cut is along this dimension. So 2 cuts means 3 pieces along this, 1 cut means 2 pieces along this. And total number of pieces is multiplication of the pieces along the dimensions, as we observed in the previous slides. So total number of pieces in this case will be 6. Now just count the number of pieces here. 1, 2, 3, 4, 5, 6. So total number of pieces we have here 6, and it can be observed as this 2 into 3. Now we have to continue this conclusion in the next form also, and that is if these three cuts are applied along all of the three dimensions. So just look at this one. If these three cuts are applied along three dimensions, then one cut along each of the dimensions and one cut gives two pieces along each of the dimensions, and total number of pieces is the multiplication of these pieces observed along the dimensions. So total number of pieces can be written as 2 into 2 into 2, that is equal to 8. Just look at this figure here. One cut along this dimension, one cut along this dimension, one cut along this dimension. There are two pieces here, there are two pieces here, there are two pieces here. 2 into 2, that is making here 8. Now just check here, just count how many pieces we have. 1, 2, 3, 4 in the upper slice, and similarly there will be 4 more pieces in the lower slice. The total number of pieces here is how much? 4 plus 4, that is equal to 8 pieces. Okay, so this observation is now complete, that number of cuts, if applied along one dimension, then the number of pieces along that dimension is equal to 1 more than the number of cuts. Number of cuts plus 1. And if number of pieces are available along the dimensions, okay, different dimensions, then total number of pieces can be obtained by multiplying these pieces along the three dimensions. Okay, and now in this way we can make this observation here. So when we have three cuts, 3 plus 1, 4 pieces along because of only one dimension, two dimensions, two cuts along one dimension, one cut along one dimension. So 1 plus 1, 2, 2 plus 1, 3, 3 into 2, which is equal to, now 1 each of the three dimensions. So 1 plus 1, 2, 1 plus 1, 2, 1 plus 1, 2. That makes it 2 into 2 into 2. That is equal to total number of pieces equal to 8. I hope this is clear. So this is the observation. This is the example I have taken, and now we are going to conclude here. Okay, that is, suppose the total number of cuts along the three dimensions are A, B, and C. Number of cuts A, B, and C. So if A number of cuts is applied along one dimension, number of pieces along that dimension is A plus 1. If B cuts are applied along other dimension, then the number of pieces along that dimension is B plus 1. Similarly, C cuts gives us C plus 1 pieces along the third dimension. And since the total number of pieces can be obtained by multiplying these all, so that gives us A plus 1 into B plus 1 into C plus 1. That is the generalization we can make. So just look at this here. Number of pieces equal to A plus 1 into B plus 1 into C plus 1. Where A is the number of cuts along one of the dimensions, B is the number of cuts along the second dimension, and C is the number of cuts along the third dimension. Okay, so that is the observation, that is the conclusion we have made till now by taking an example and generalizing that example. I hope this is clear. So if cuts are A, B, and C, fine, these are along the different dimensions, then the number of pieces can be obtained as A plus 1 into B plus 1 into C plus 1. If I have to find out how many cuts are here, so total number of cuts can be, total number of cuts will be written as sum of these A, B, and C. Total number of cuts we have here, A plus B plus C, and accordingly the total number of pieces is equal to A plus 1 into B plus 1 into C plus 1. Fine, I hope this is clear. Now I'm going to start with one question from the handout, and just look at the question number 1. Question number 1. What is the number of pieces into which a cube can be cut by 3 cuts in one dimension, 6 cuts in the second, and 7 cuts in the third dimension? Now 3 cuts along one dimension. The number of pieces along that dimension is how much? 3 plus 1. 6 cuts along the second dimension. So number of pieces along that dimension is 6 plus 1. 7 cuts along the third dimension. Number of pieces is equal to 7 plus 1. So the number of pieces along the dimensions are obtained as 3 plus 1, 6 plus 1, 7 plus 1. Fine. So total number of pieces can be equal to 3 plus 1, that is multiplication of these all pieces we have obtained here, and that is 4 into 8 into. Now 4 8s are 32 and 32 into 7. 16 7 are 112. 112 into 2 is giving us 224. Right? Total number of pieces in this case to be obtained as 224 and our answer choice will be B. Now look at the solution here. 3 cuts in one dimension, 3 plus 1, that is 4 pieces. 6 cuts in second dimension, that is 6 plus 1, 7 pieces. 7 cuts in third dimension, that is 7 plus 1, 8 pieces. And total number of pieces can be obtained by multiplying these pieces along the 3 dimensions. And that is here 4 into 7 into 8. That gives us how much? 224 pieces. And our answer option will be ticked as. I hope this is clear. Now, move on to the next part. That is, some theory part is appearing here. And we have to just do some conclusion. Okay. So, the next theory part here we have as, suppose the number of cuts is constant. As we have seen in the case of 3 cuts were applied in the beginning, we have seen, then there were 3 possibilities. It depends upon the types of the cuts, the way in which we provide the cuts actually. So we had seen that when all these 3 cuts were applied in the 3 dimensions uniformly, okay, we got the number of pieces maximum. Fine. So this conclusion can be applied here. Okay, fine. So suppose if I am talking about 6 cuts, total 6 cuts are applied. A plus B plus C equal to 6. For example, if the total number of cuts is constant, and that is A plus B plus C equal to 6, if I may suppose. I'm just taking one example to explain first. Okay. Then the distribution of these cuts will be different here. There are many possibilities like 006. So 006 is one possibility, and 015 is another possibility, 024 and so on and so forth up to 222 is the next possibility. Fine. So when I have taken 222, the number of pieces is 2 plus 1 into 2 plus 1 into 2 plus 1, that is 3 into 3 into 3, which is equal to 27 pieces. Now if I have taken this distribution 006, then the number of pieces is 0 plus 1, 0 plus 1, 6 plus 1, that is 7 pieces. So we can make one conclusion here that if number of cuts is constant, then the number of pieces is maximum when these A, B, and C, these are A, B, and C are the cuts along the 3 dimensions. So these A, B, C are as close as possible as we had seen in the case of 2, 2. So if these A, B, C number of cuts are as close as possible, then we get the maximum possible number of pieces obtained. And if these cuts are A, B, C are as far as possible, then we get a minimum number of pieces obtained. Okay. So this is the conclusion we have here in the generalization form, where A, B, C are number of cuts in the 3 dimensions. The number of pieces is maximum when A, B, C are as close as possible. Okay. And number of pieces is minimum when the A, B, C are as far as possible. I'm just trying to explain by one more example. Okay, let's take one example here. Total number of cuts, suppose 14. It means A plus B plus C is equal to 14. I have just taken an example. So what is the way to find out the maximum number of pieces? So maximum number of pieces we have the conclusion that A, B, C should be as close as possible. How to obtain that number? Divide 14 by 3. Divide 14 by 3, quotient will be 4. So 4, 4, 4. So this distribution will be like 4, 4, 4. Now the remainder is 2. Now this 2 should also be divided equally in as many directions as possible. Okay. So this 2 can be divided in 2 more directions, and that is 1, 1. So this distribution further will be here as 4 plus 1, 5, 4 plus 1, 5, and then 4. So this distribution will be like 5, 5, and 4, or 4, 5, 5. So maximum number of pieces is possible when these numbers are very close to one another, and in that case the distribution of ABC will be like 4, 5, and 5. I hope this is clear. And in that case, number of pieces obtained will be 4 plus 1 into 5 plus 1 into 5 plus 1. That gives us 5 into 6 into 6, and that is equal to how much? 180 pieces we can obtain as maximum number of pieces. I hope this is clear. Now, similarly, if I go for minimum number of pieces, so as per the conclusion, this number should be as far as possible. So if nothing special is mentioned, then the distribution will be like 0, 0 and 14. As far as possible is there. So 0, 0, 14, and in that case, this distribution will be like 0 plus 0, 0, 14, and the number of pieces will be 0 plus 1 into 0 plus 1 into 14 plus 1, which is equal to 15 pieces. I hope this is clear. So in that case, the number of pieces 15 is the minimum possible number of pieces we can have. Okay. So if I look at this 0, 0, 14, I can say all the cuts are applied along one dimension. And in the previous case, all the cuts were applied along the three dimensions. Okay. Now, suppose a condition is made as, condition is given as each of the cuts, each of the dimensions have at least one cuts. Suppose that condition is here. So at least one cut along each of the dimension. Then what can happen in this case? Okay. Since a condition is provided and we have to go for as far as possible. So give 1, 1 to each. So by giving 1, 1 to each, we have the remaining part as 11. Now to maximize the difference as far as possible condition, then give 11 to exactly one of the dimensions. So the distribution will be like 1, 1 and 1 plus 11, that is 12. So in that case, as far as possible will satisfy when we assume A, B and C in the way of 1, 1 and 12. Now accordingly, the number of pieces will be 1 plus 1 into 1 plus 1 into 12 plus 1. That gives us 2 into 2 into 2. That is equal to 2 into 2 into 13. That is equal to 4 into 13, which is equal to 52 pieces. So in that case, if at least one cut is provided along each of the dimension, then total number of pieces as a minimum can be obtained as 52 and a maximum we can have as 108. Okay, this is the theory part we have, and that was the example. So now look at the question from the handout. Look at this here. What is the maximum number of pieces into which a cube can be cut by 19 cuts? Okay, just use the same funda. 19 cuts. So to maximize the thing, we have to distribute these 19 cuts in such a way that these numbers A, B, C are as close as possible. So for that, what we do, we divide this by 3 and the quotient will be 6. So this distribution will be like 6, 6, 6 and one remainder can be given to any one of these 3. So that makes the distribution of the cuts as 6, 6 and 7. I hope this is clear. And in that case, the total number of pieces can be obtained as 6 plus 1 into 6 plus 1 into 7 plus 1. So 7 into 7 into 8. 7 into 7 is 49. 49 into 8, that gives us 392. Okay. I hope this is clear. So just look at the solution here. Total number of cuts is A plus B plus C, that is 19. And the distribution will be for maximum as 7, 6 and 6. Fine. So the total number of pieces will be as 7 plus 1 into 6 plus 1 into 6 plus 1. Okay, fine. And the total number of pieces can be obtained as 8 into 7 into 7. Fine. 8 into 49 will give us, that is 392 pieces. And the answer option to be ticked here as D. I hope this is clear. So the answer option we have here as D. Now, lateral discussion can also be better for us here. That is, if there is a question of minimum number of pieces when at least one cut is applied in each of the dimensions. Just we have discussed in the previous example here, previous slide. So what we will do here, just apply 1, 1 cut first. So 1, 1 cut, remaining 16. 16 all should go to exactly one dimension. The distribution will be like 1, 1 and 7. Okay. So if that is the condition, then the number of pieces being minimum when the distribution will be as 1, 1 and 17 for A, B and C. Now the number of pieces can be obtained as will be how much? 1 plus 1 into 1 plus 1 into 17 plus 1. I hope this is clear. And that 1 plus 1 into 1 plus 1 into 17 plus 1 makes us 2 into 2 into 18. Okay, and that gives us 2 into 2 into 18 gives us here 72. So total number of pieces is equal to 72. Minimum pieces is 72, and this is here 18 actually, not 13, this is 18. So 2 into 2 into 18, that is equal to 72. If this is the question asked here for minimum, then its answer would be in that way, that is 72. But we had the question for maximum, so our answer obviously was D for this question. I hope this is clear to all of you. Now, the next learning is to reverse this process. That is, in this case, we had here number of cuts constant and number of pieces minimum and maximum were to be discussed. Now, suppose we have number of pieces constant. Okay, then the number of cuts is to be minimized and number of cuts is to be maximized. Since the process is reverse, the result, the conclusion is also reverse. Okay, what I mean to say is, just look at this here. If total number of pieces is constant, that is a plus 1 into b plus 1 into c plus 1, that is constant, where a, b and c are the number of cuts in the 3 dimensions. Fine. Total number of cuts will be a plus b plus c. So if I look at this a, b and c, these are one less than the number of pieces here. So whenever number of pieces is constant, first we factorize it, and the factor whatever obtained here subtracted by 1 to get here a. B plus 1 is another factor and b is 1 less. C plus 1 another factor, c is 1 less. So total number of cuts, if I have to calculate, we have to subtract each of the factor by 1 and then add it. Okay, so total number of cuts are obtained in that way. Okay, I hope this is clear. Now conclusion is just the reverse of the previous conclusion. That is, if you want to maximize the number of cuts, so maximum number of cuts is possible when this distribution of A, B and C is as far as possible. I hope this is clear. So just in the reverse of the previous conclusion. So to maximize the number of cuts, is A, B and C should be as far as possible. Fine. For minimizing the number of cuts, this A, B and C should be as close as possible. This is just the opposite of the things we have discussed in the previous case. I'm just trying to explain by one example. Suppose the total number of pieces is 60. So suppose number of pieces here is assumed to be 60. So in that case, I can assume this as A plus 1, fine, into B plus 1, okay, into C plus 1, that is total number of pieces. Now maximum number of cuts is possible when these are as far as possible. It means the factorization should be like 1 into 60. Okay, so these are possible when we have A plus 1 is 1, B plus 1 is 1 and C plus 1 as 60. I hope this is clear. So in that case, A plus 1, B plus 1, C plus 1 are to be distributed as 1, 1 and 60. Total number of cuts here is A, B and C, A plus B plus C. So total number of cuts can be obtained here. From this one I can get 0. From this one I can get 0. Why? A plus 1 is 1, then A is 0. B plus 1 is 1, then B is 0. C plus 1 is 60, then C is 59. It means total number of cuts will be equal to A plus B plus C plus C, and that is 0 plus 0 plus 59, which is total number of cuts applied is maximum number of cuts, that is 59. I hope this is clear. So in this case, I already have said whatever the factors we are getting, that is 160, the number of cuts correspondingly can be obtained by subtracting 1 from each of the factors. That is 1 minus 1, 1 minus 1, 60 minus 1, giving us 0 plus 0 plus 59, which is 59 maximum cuts are required in this case. Okay, fine. Now similarly, when I go for minimum cuts, the condition we have here as these A, B and C should be as close as possible. Fine. So by doing this factorization, you will find 3 into 4 into 5 is the best possible for A, B and C being as close as possible. So A plus 1, B plus 1, C plus 1 should be like 3, 4 and 5 for minimum number of cuts. Okay. So A plus 1, 3, B plus 1, 3, A plus 1, 3, B plus 1, 4, C plus 1, 5. I hope this is clear. In that case, A, B and C can be obtained by subtracting 1. Since A plus 1 is 3, A will be 1 less than 3. Since B plus 1 is 4, B will be 1 less than 4. Since C plus 1, 5, C is 1 less than. So the total number of cuts can be obtained as 3 minus 1 plus 4 minus 1 plus 5 minus 1. I hope this is clear. And that gives us 2 plus 3, 5 plus 4, that is equal to 9 cuts. So minimum number of cuts required in this example is here how much? I hope this is clear. So this is the conclusion. I repeat this conclusion. If total number of pieces is constant, then the number of cuts can be maximum if this distribution of the cuts are as far as possible. And this is possible for maximizing when we go for all the cuts along only one dimension. As we have seen here, 0, 0, 59 means 0, 0, 59 means all 59 cuts are along one dimension and total number of pieces is 59 plus 1, that is 60. So maximum number of pieces, maximum number of cuts can be applied along one dimension, and that is 59 cuts are applied. So overall maximum number of cuts is possible when we apply along one dimension. I hope this is clear. For minimizing the cuts, obviously the distribution should be along as many dimensions as possible, and in that case we obtain the minimum number of cuts required when these are as close as possible. I hope this is clear. Now I am going to discuss with the next question of this handout, that is question number 10 of this handout. What is the minimum number of cuts required to cut a cube into 294 pieces? So 294 pieces. So we have to factorize it. Now look at this first of all. This number is 294. Okay. So this number is obviously divisible by 2. That is even number because of even number. And now just take the sum of the digits, and that is 15. It means this number is divisible by 3 also. Overall, this number is divisible by 6. When you divide it by 6, the remaining remaining part of 294 will be 49. Now, this is very clear that 49 can be written as 7 into 7. So to minimize the number of cuts, this distribution of the pieces should be as close as possible, and that's why we can have, this is the way of factorization. I hope this is clear. So when we factorize 294, we get here 776 in the form of as close as possible. And for minimizing the number of pieces, we have to distribute this in the way of 776. Now corresponding cuts, 7 minus 1 6, 7 minus 1 6, 6 minus 1 5. I hope this is clear. The total number of cuts required is how much? 6 plus 6 plus 5, that gives us 17. 17 cuts are required. Fine. So the answer choice to be picked for this question is A. So just look at the solution. Total number of pieces we have 294. Minimum number of cuts is possible when these are as close as possible. And we have A plus 1, B plus 1, C plus 1 as 776. Then corresponding A, B and C can be obtained as cuts here as 7 minus 1, 7 minus 1, 6 minus 1. That gives us 6 plus 6 plus 5, that is 17 cuts. So the answer choice for this question is A. Now, suppose the question was to find out the maximum cuts. As we have observed that the maximum number of cuts can be obtained when these cuts are as far as possible in the way of distribution. Means, in this case, all the cuts should be along one dimension. So for 294 pieces, we need 293 cuts. Okay. Or the distribution will be like 0, 0, 293. Factorization will be like 1 into 1 into 294. and accordingly we get 00293, and that is total 293. Maximum cuts are required to get 294. I hope this is clear. So now we have seen here cuts and pieces based questions. Now next type of question we have here is coloring of the large cube, and then it is cut into some pieces by applying minimum cuts, and after that we have to find here how many pieces are with three face colored, how many pieces are with two face colored, how many pieces are with one face colored, and how many pieces are with no face colored, zero face colored. I hope this is clear. So just look at here this example. So a cube is painted and cut into 343 smaller but identical pieces by the minimum possible number of cuts. Minimum possible number of cuts if are applied, okay, then this is possible when this distribution of the pieces along the dimensions are as close as possible, and cuts are also as close as possible. Like 7 into 7 into 7 is the distribution of the pieces along the dimensions. 7 into 7 into 7 means the number of cuts required as 6, 6 and 6 along the 3 dimensions. I hope this is clear. So after doing this, we can have the figure of the cube like this one. It appears as this one here. So just look at in along this dimension, how many cuts? 1, 2, 3, 4, 5, 6 cuts applied, and the pieces we have 1, 2, 3, 4, 5, 6, 7. 7 pieces along this dimension. Similarly, 1, 2, 3, 4, 5, 6, 7. 7 pieces along this dimension. Similarly, 1, 2, 3, 4, 5, 6, 7. 7 pieces are along this dimension. So this is the way in which we can apply the minimum possible cuts, and total number of pieces are 343. Now, the question is of 3 face painted, 2 face painted, 1 face painted, no face painted. Just try to look at this figure here. How many pieces we have? 343. And for 3 face painted, we have to look for that position where the exposure of 3 faces are there. So just check this one, this piece. You will see here this piece has 3 exposure faces, the exposed faces, that is 1, 2 and 3. It means if I take this piece will have 3 face painted. Fine. So it means, can I say the 3 face painted pieces are lying at the vertices? Yes. So these 3 face painted pieces are lying at these vertices. And how many vertices we have? 8. And at each of the vertices we have one such type of pieces. The total number of 3 face painted pieces will be how much? 1 into 8, that is equal to 8 pieces. I hope this is clear. So 3 face painted pieces will be how much? 8. Now, similarly, if I talk about 2 face painted, so this was 3 face painted, this was 3 face painted, 3 face painted. Now just look at this type of neighbor of this type of piece. It has here 2 face open towards painting. So 2 face painted, 2 face painted, 2 face painted, 2 face painted. Can I say these pieces are lying on the edges? So 2 face painted pieces are lying on the edges. Okay. And out of those 7 pieces on each of the dimensions, since 2 vertices based pieces are removed here, the remaining number of pieces available at the edges will be how much? 5. So 5 pieces are along each of the edges. Total number of edges we have how many? 12. We already have seen. So the total number of pieces with 2 painted face will be 12 into 7 minus 2, that is 5. So 12 into 5, that gives us 60 pieces. Okay. So total 7 pieces, 7 minus 2, 5 pieces along each of the edges, and total number of edges we have 12. So total number of pieces with two face painted will be 12 into 5, which is equal to 60 pieces. I hope this is clear. Now, similarly, if I go for one face painted, so these are now all removed from the list because two face painted are removed, three face painted are. Now look at this one. The pieces lying at the faces are having only one face open or exposed towards the painting. So these are here one face painted category based. So these can be categorized as one face painted type of pieces. Okay, and these are lying at the faces. Okay, so now how many pieces are available? 5 pieces along this dimension, 5 pieces along this dimension. So 5 into 5, total we have 25 pieces along one of the face. Total number of faces is how much? 6. So 25 into 6, there are 150 number of pieces which have only one face painted. I hope this is clear. Now, no face painted, all will be lying inside it. Now, these all exposed pieces are acting as a layer for those pieces which are lying inside it. And how can it be considered as layer? These one piece along the dimension. So if this, suppose if I talk about this, if I remove this one, this is upper layer, and if I remove this one, this is lower layer. So if these two are removed, then can I say the no face painted will be lying inside it? Similarly, from this side, one layer is removed. From this side, this layer is removed. Okay. So 5 are remaining here. And from this is removed. And from back one, this is removed. So if these layers are removed, the remaining portion is here the pieces with no face painted. Okay. And this looks like this one. Okay. 5, fine. 5 and 5 along this. So 5 into 5 into 5, there are total 125 pieces, which are no face painted. I hope this is clear. So now I am going to explain it again here. When a cube is cut into 343 pieces, okay, by applying the minimum cuts, then distribution of the cuts are as 7 minus 1, 7 minus 1, 7 minus 1, 6 plus 6 plus 6, that is equal to 80. Three face painted pieces lie on vertices, as we have observed here. That is, number of pieces is 1 into 8. Why? Because the number of vertices we have as 8. One piece at each of the vertices. Now, total number of three face painted pieces is 8. Two face painted pieces are lying on the edges, and number of pieces on each of the edges is 7 minus 2, that is 5. Number of edges is 12. So 5 into 12 gives us, that is 60 pieces. So 60 pieces are two face painted pieces. Okay. Similarly, if I go for one face painted pieces, these are lying on the edges. These are lying on the faces actually. And on each of the face there are 25. 7 minus 2 into 7 minus 2, 25, and there are 6 faces. So 5 into 5 into 6 gives us 25 into 6, that is equal to 150, which are one face painted. No face painted are lying inside this, that is acting as a crux of this one, and that is here no face painted pieces are lying completely inside it, and that is 7 minus 2 into 7 minus 2 into 7 minus 2, 5 into 5 into 5, 125. This is the conclusion we have made before the question starts here, and we have got the answers here. Okay, now look at the question. First question of this 15th question of the handout. How many smaller pieces have exactly 3 painted faces? Okay, now whatever the conclusion we have made, if I tabulate it, it will be looking like this one. So now it can be tabulated as this one. First is 8 cornered pieces, exactly 3 painted surfaces, 8 cornered pieces. So the number of such pieces is equal to C. So how many smaller pieces have exactly 3 painted faces? That is 8, and the answer choice is here C. That is the answer of question number 50. I hope this is clear. So we already have observed that is 8. That is answer choice. Question number 16. Question number 16 is about here. How many smaller pieces have exactly two painted faces? And exactly two painted faces are lying on the edges. Just look at this here. 7 minus 2 into 12. That gives us 5 into 12. Exactly two painted surfaces. 5 into 12 which is equal to 60. The answer choice to be ticked as. Now, next question. How many, I hope this is clear here. How many smaller pieces have exactly one painted face? One painted face are lying completely inside, and that is we already have seen as one painted faces are lying on the faces actually. Okay, I make it clear. Okay, I correct it that one painted faces are lying. One painted face pieces are lying on the faces. We already have discussed in the previous slides, and these are lying at the faces. That is 7 minus 2 whole square into 6. That makes it 150. Exactly one painted surface, and that is answer choice B. I hope this is clear. Now, question number 18. So, no, in this case, no painted face, and that is lying completely inside. We already have discussed here question number 18. That is no painted surface n minus 2 whole cube 120. That is our answer choice B. I hope this is clear. So, till now, we have discussed the basics of this. And we can generalize here one more thing that if the total number of pieces along one of the face is here we have 7, and if I generalize it as n, so n equal to 7, then we can write it as number of 3 painted faces as 8. So n cube, total number of pieces can be written as n minus 2 plus 2 whole cube. And if you expand with the help of a plus b whole cube, you will get this expansion as n minus 2 whole cube plus 3 into 2 into n minus 2 whole square. Then we will get 3 into 2 square into n minus 2, and after that we will get n minus that is equal to n minus 2 whole to the power 0. So that is actually 2 raised to the power 3. Right? So we have n minus 2 whole cube plus 3 into 2 into n minus 2 whole square plus 3 into 2 square into n minus 2. Gradually the power of 2 is increasing, and that is 2 cube. So 8. This represents 3 face painted. This represents here edges like 3 4s are 12 lying on the edges. So this is 2 face painted. Okay. This represents here 1 face painted, and this represents here no face painted. Okay. So this is the thing we have learned as a basic. Okay. So I'm going to end this session, and in the next session we will discuss with the better question, means the questions with higher difficulty level of this handout. I hope this is clear. Fine. Thank you.